All right. So cross product. Um, it. This is one way. There's several different ways. I was taught somewhere a different way than you guys are taught. It's the same. It yields this thing here. So what it does is it takes the component. You have two vectors, multiply them to each other. Oh, put it earbuds or something. I don't know. Don't be distracted. It takes the component of one of these vectors that is perpendicular to the other one and multiplies them, and the that's the magnitude of it. The direction, a cross product will yield a vector. The answer will be a vector that will be perpendicular to both of these vectors. So let's say the vector is going like this. The plane that these vectors are in, that cross product will be a vector that is perpendicular to both of those. It will be perpendicular to that plane. Okay, specifically orthogonal to that plane, and that's where the right-hand rule comes from. Okay, and why we use the right-hand rule. Either this way, like here's the plane of the two the two vectors were multiplied, and the direction of that the product of those is going perpendicular to that. Or when we use the right-hand rule with the electromagnetic stuff, we always have X, Y, and Z axes. Okay, Sam.
Is there a conceptual reason for that, or is that just notation?
So with rotational motion, that's just kind of a convention that we've used. With electromagnetic, it actually physically goes that way. So, all right. So, when you do the cross product, so we have a force. So you have a wrench. That's a meter long. Okay, and you're exerting a force at 53 degrees, 5 newtons. Okay, you're going to find the component of force that's perpendicular to that. That's going to be your force perpendicular to 1 meter. So you should have, it should be 4 meter newtons. Okay, so we're going to test that out. So this is in terms of units, sorry, not units, in terms of rectangular coordinates. So the way you're going to write that, it should be 100. That would be a really long wrench.
1 meter is still.
It is. It's. I mean, I've seen those before. Like a breaker bar trying to like do lug nuts on a car. Okay, so a two-dimensional. No, we'll just go 3. I'll show you 2 because this is what we're usually using in here, but for kicks and giggles, I'll show you 3. So here's the radius, here's the force. 2x2 matrix. Okay. What you're going to do is you're going to multiply those two, 1 times 4, and then minus 3 times 0. Okay, and what this yields is 4, and you know because it's just a 2x2 matrix that it's going to be in this is the x, this is the y, so this is going to be in the z direction. So okay, this only works when it's two dimensions. You got the x, you got the y, so the third one has to be, the answer has to be in the z direction. Okay, typically when you do this, and this is where I was taught differently and you guys are being taught. Here's how I would set this up. Is everybody okay with that? You won't ever, I'm teaching you stuff that you wouldn't have to do on the AP test. This is just trying to tie in math and the real world. Okay. So what you're going to do for a 3x3 matrix is you're going to do this. Oops, sorry. I, J, K, 0, 0. This is the way that Clumpy taught it. I'm fuzzy. You're gonna have to help me on the plus or minus. I'm fuzzy on that one. Okay, so I'm gonna cover up this. Oh, start with I, huh? Start with I. See, I'm pretty already fuzzy. Start with this, and then you go 0 minus. So you go 0 times 0. I'm just trying to be explicit here. Minus 0 times 4. Okay, and that's going to be your I quantity. Is that right? Okay, that's your x component of that vector. And then minus. Okay, thank you. And then you cover up this column, and then you go 1 times 0 minus, bless you, 3 times 0. J hat. Okay. And then plus, cover up the K, and go 1 times 4 minus 3 times 0. And that's going to be K hat. I should, thank you. And so you end up, this is 0, 0. This becomes 4 minus 0, and just 4K. Okay. Here's how I learned it. I'm just giving you this is just, you won't have to do any of this. Here's how I learned it. This is for funsies again. I learned it. You write up this 3x3 matrix, and you go I times 0 times 0 plus J times 0, and then you do like Pac-Man, playing Pac-Man, you go through one, and so it goes through the wall, times 3. K times, goes through the wall, 1 times 4. Okay, minus all of this. You go the other way. You go k times 0 times 3, and j times 1 times 0 or plus I times.
I think you should be subtracting I. I don't know.
No, this is all quantity. All the red stuff was negative.
Okay.
So for me, I don't. The way I learned it, I don't have to memorize. You subtract. Everything going this way is minus that big quantity. That's all negative.
That should work, but
It works.
it seems way more
I would hope
complicated.
it. I trust it, and that's
Why
cool.
why isn't it?
Yeah.
Okay. So you pick. There's multiple different ways to do that. Okay. Cross products. Okay. So you could do it with bigger things than that, but I'm not.
A cross product doesn't really work in 4, 5, or 6 dimensions.
Correct.
There's a reason I stopped at 6.
Okay. So static equilibrium. This stuff will be on the AP test. Okay. So when something is in static equilibrium, we know that the sum of the forces are equal to 0 and the sum of the torques are equal to 0. If you go into civil engineering, this is going to be your life, because we do not want buildings and bridges to be experiencing acceleration.
Constant acceleration.
Zero. That's all I care about. Okay. So this is reality, X, Y, and Z in all directions. In this class, we're limiting it to problems that are going to be honed in a plane of a piece of paper. So you got the sum of the forces in the X direction equals 0, sum of the forces in the Y direction are equal to 0, and some of the torques in the Z direction are equal to 0. Okay. I introduced this to you last year a little bit. So one of the things is you can pick your axis of rotation, your origin, to be anywhere along this. It doesn't matter. However, there are some places that are more strategic than others. Okay. I'm pretty sure I gave you this example last year, but we will work this out. So we've got a meter stick that has mass, and we're suspending a mass from the end of it, or sorry, from the 80 centimeter mark. Where should we put the fulcrum to balance it? Okay, so we have, I think I gave you this disclaimer as well last year. This gets sloppy, but everybody does it, so we'll just go with it. This technically is a force of tension acting on the meter stick, but because it's in equilibrium, that tension is equal to the force of gravity of the mass. And so people just go straight away and just say it's equal to mg. I'm not, but is it, if everybody's good, like that's just the common accepted thing, like when you go to college. Okay, so you've got a normal force from the pivot, and then we also have at the center of mass, we have the force of gravity Okay, so we're drawing an extended free body diagram. We can pick anywhere along here to be our axis of rotation.
I pick the far end of the object.
Okay, so we could probably the place that most of you guys would pick would be here.
The place where it is.
But we don't know that. We're looking for that.
So it would be God.
Okay, we're gonna make that the origin. Okay.
What about the left edge?
I'll show you. We'll pick a different spot just for proof of concept. Okay. So I know. Let's see where I want to go. What's the room here? I know that some of the forces in the x direction are equal to 0. There's none.
Which way
Okay.
y, which way z?
So we'll say no, I'm just gonna positive x, positive y, and positive z is coming out of the page. Okay. Some of the forces in the y direction are equal to 0. So I've got normal force minus little mg minus big mg is equal to 0. And I have the sum of the torques about this axis rotation are equal to 0 as well. So
The torques are exactly.
So what we're gonna so I know that this is 0.5 meters to here. I know this is 0.8 meters to here. What I am looking for is, we'll say x. Looking for this. There I go, that. So this distance is going to be this, the way that that's going to make it rotate this way, which we'll say is positive. So it's mg, that's the force, times x minus 0.5 meters. Okay, that's the torque from this guy. And then this one wants to make it rotate the other way. So minus capital mg times, and then this distance is going to be 0.8 minus x. And that's equal to 0. Okay, go to that. Now, with this, I can solve this with just that. Okay, the only unknown I have is x. So,
I was thinking that you said that.
Technically is.
Well, yeah, it's multiple equations, so yes, it would be.
okay. So, we get that to be mg.5 plus mg.8 over.
You can actually factor out a G.
Could factor out a G, and that'd be a good idea. Let's go ahead and do that. I like it. Okay, so
Since you crossed out the G, so you should probably put a G in front of that just so that you can cross it out. I guess you can put it behind as well.
okay, and then we get proof of concept. We get 0.25 times 0.5 plus 0.5 times 0.8 equals divided by 0.75. I got 0.7. Anybody want to
Yeah, that makes sense.
validate that one?
The right number is 6 big for smiling.
Absolutely.
What is this, chemistry?
No.
Actually, you do teach chemistry, so that was bad.
There we go. There we go.
Well, actually, I'm pretty sure it should just be one.
Yeah. 80.
7.50.
Yeah, that's true. I had it right. That was good. That was good. No, you're good, man. It's always good to be challenged. All right, so that's one way to do it. Another way would be, make that side your axes.
And then you don't have to worry about all that subtraction.
Yeah, you don't have to worry about the subtraction. So, but you will have to incorporate this. So you just like mg times, that wants to go that way, negative 0.5 plus normal force times x minus mg times 0.8 equals 0.
Something's wrong there because with that you have. Oh wait, never mind. No, it's right.
Okay. So you'll have to find normal force with this.
So it's a system of equations.
And then stick that in here. And then you're set to go.
You don't have to remember subtraction.
Yeah, but you have to remember to set up a system of equations and solve it, which sounds so much worse.
You pick your poison.
Subtraction
Okay.
is much worse.
Preference. All right, so that was a review. Last year all you did was one dimension. Like it was just the sum of the forces in the usually the sum of the forces in the y direction have to be equal 0. You had, it was this type of problem. That's what you had last year. Okay.
Why would a ladder have a roller on it?
Okay. There.
It's so contrived.
Okay.
I love this.
No, I have used a ladder with a roller on it before. Okay, that's so that you don't scrape the side of the house. No, it's not stupid. You say it's stupid until you like scratch your house you're painting, like yeah, just paint over it. So the roller. Anytime you have a roller, what this does is you only provide one force going this way, just a normal force. Okay, there's no friction. Does that make sense? So when you see a roller, you should be happy because there's only one force that's perpendicular. It's just a normal force. There are, when you make bridges, they do to do like expansion and contraction. Okay, there's one of these joints that's movable. I've seen them I've seen it where they had a rocker. Okay, you'll find these on steel bridges more than concrete, but
It's just smiling.
yeah,
Won't the ladder be more as we gotta slow down?
it will be more apt to slip.
And instead of instead of a roller, why don't you just make it so like it's like some flat surface attached to a ladder at the very end?
So in reality, what you have are called ladder mitts, and they're like squishy. They don't screw.
No rollers.
It makes your problem harder. I'm just telling you, when you get a roller, you should be happy. Okay.
I wasn't complaining about the question. I was complaining that it's contrived. There's a difference between the two.
I have used a ladder with a roller, like physically.
Have you had a ladder with a roller on both sides?
No.
I like it.
Okay. So what you have, we're doing an extended free body diagram of the ladder. So you've got the weight of the ladder in the middle. You got the weight of the guy.
Oh, I love the guy.
We don't know where the guy is.
Position X.
Okay. And we also have here, we have a normal force. Yep. 212 pounds. Not crazy.
Yeah. More than double my weight.
Well.
Friction acting on the bottom end of the ladder.
Okay. So there is friction on the bottom of the ladder. And which way is friction going? If you put it on ice, which way would the end of the ladder go? The ladder would go this way. So friction opposes that and goes this way. Okay? And we're going to say that's maximum static friction.
Okay, we're asking for how high up, so fine.
Okay?
Oh, that's cool.
Does that make sense? Have you ever been on a ladder? Okay? Have you ever been in a precarious situation where the ladder is like tilted out and you're like, oh man, if I go too high, I feel like it's just going to like kick out and poof.
That's
I've had it fall over on the side for that.
I don't think. Remember, I don't think about things before I do them. So that
Okay.
problem never comes across.
That's a thing. So that's why you have people stand on the base of your ladder to keeping that from kicking out. All right, so some of the force in the x direction are equal to 0. So we've got the normal force. Oh, we need to specify. We'll say
W and L. W for the wall and L for the ground.
Roller and
L.
Yeah, for the ground.
Ground.
G.
G. We'll go. I'll go W and ground. That's.
No, that's gonna get too confusing. That's why I choose L, because G gets confusing with G.
But L can be confused for light.
Okay, so we have normal force from the wall minus maximum friction is equal to 0. Some of the forces in the y direction are equal to 0. So we've got normal force from the ground minus the weight of the ladder minus the weight of the guy is equal to 0. Okay. Name the guy Fred. Some of the torques are equal to 0. Different Greg. Yeah.
I was wondering why there were two MGs. Yeah.
Okay.
But they were like on both his feet, and I was like,
Oh, that's why. I thought they were just both from his.
Yeah.
Oh, sorry. No, the weight of the ladder. It's true.
And there's some from his hand.
All right.
Yes.
We're gonna just specify at the center of mass of the dude.
His mass is
So where do you want to make the pivot? Where do you want to make your?
The wall.
The wall.
Well, it's
argue,
either
yeah,
hardware
definitely the wall.
restriction Zach thing.
I agree with
1
I
meter.
agree with the
I
wall.
do disagree.
No, I agree with the wall.
My suggestion would be this, because that gets rid of two forces.
That's not why I'm doing it. I'm doing it for a really stupid reason. Because then the distance, you just have to undo the angle, and then there you go. You get
All right, so we know that this is 3 meters. This is 5 meters, so I was nice to you. And this is 4 meters. Okay. So, line of action.
Well, first off, it's not going to be.
This is the only force that's making torque go this way. Normal force from the wall. So we have a negative normal force from the wall times 4 meters plus force of gravity of the ladder times, here's the line of action. Okay, so I know this is 2.5 meters. This is 1.5 meters.
So it's probably 2 meters.
This is 2 meters. The line of action, the radius, sorry, the lever arm would be 1.5 meters. Everybody okay with that? 1.5 meters plus mg times, I'm just going to say x. X being, this part? Okay, so the force of gravity is acting at the center of mass of the ladder. And so the line of action goes down through here. This side of this triangle is 2.5, is half of that. Therefore, like similar triangles, still a 3, 4, 5 triangle. This is 1.5, this is 2 meters. Okay, and I'm looking for this. I'm looking for this lever arm here. That's my x. That's not going to be my final answer.
Yeah, I would a different way so that X is my final answer.
Well, you could do that.
It requires dot products.
It doesn't require it. You could do that.
Okay, sorry, it doesn't require it, but I would use dot products because I'm lazy.
That's why. It's good. It's always good. All right, so here's our setup. I've got two unknowns. I don't know my normal force from the wall. So I look over here and I say normal force from the wall is equal to maximum static friction. So that's coefficient times the normal force from the ground, which I don't know that, but I do know that the normal force from the ground is equal to the sum of the weight of the ladder and the guy. Coefficient. Oops. There. Okay. So I can plug that in here. That's 4 meters. And get rid of G's. So that is going to give us, what are we at, 0.6 0.6 times 120 kilograms times 4 minus 20 times 1.5 equals.
Cooking show while Smiley was figuring out the thing.
This is true, because I used to do cooking show.
Did you not lose a negative?
Yeah, feel like I did.
You did. It's just 'cause the denominator.
You'd be dividing by negative.
All right.
So you would.
Oh, right side.
Yeah. Yeah.
That.
Yeah, no, you would divide by negative. Well, assuming that initial equation.
Oh, yeah. Thank you. Good call. Oh,
You're on the right slide.
okay. There. Thank you. Good call. Oh, boogers. Divided by.
You could just divide by -1 now, unless you got rid of your answer.
So I got.
Brad, you ready for the shot? How many times I this is I would get it. You're like, yeah, that's probably right, and make it positive. That's my
And then you get it right.
All right. So I got 2.58 meters. That's not my answer. That's how far this is.
Now you went 12 over that.
So I go cosine. No,
You don't want 12 over.
I want to do similar triangles. That'd probably be the easiest. You could do cosine or stuff, but whatever. I'm gonna do
Or is that
3/5. Why would I do that? I'm gonna do 5/3. 5/3 is equal to 2.58 over length.
Okay. Oh, so you want length along the ladder, not how high up.
How high up the ladder?
Yeah, that's asking for the height.
Up the ladder. So times 5 divided by 3 equals 4.3 meters. So pretty high up there, and then it's going to slip. Okay. Little practical tricks. So I painted in college. Trick is you take a screwdriver or a stake and stick it there. They also have some of the extension ladders have pivoting feet.
Oh yeah.
And you can rotate it up, and there's pokes on one side. You pivot up and then jump on it in the ground. Okay, good at that.
Why don't you just use a drill to drill into
Drill into the.
You're gonna drill into the ground.
Why would I use a hand drill?
No, drill into the house.
No, unless moving windows around.
Yeah. I honestly wouldn't be surprised, guys.
Yeah, fair enough. You know what I That was the first one.
I mean, that's all way.
It would definitely. I don't care about losing this though it's a left area.
All right.
I don't care about
What do we got here? 10 minutes. 10 minutes.
When you get a car, I want you to duct tape flow torches to the side of the hood and then hook it up so that every time you hit the gas, it fires.
That's not going to be legal.
Okay.
I didn't need that
Here we go. We're gonna learn some stuff.
I mostly use
Okay.
I hate learning.
I know, right? So, what we're gonna do, we're gonna focus on the members.
Red triangles are
Okay. And we're gonna do extended free body diagrams of the members. Okay.
Why would you set up something like that? Like,
It's a shelf.
yeah, why would you set up a shelf so that's hinged?
That's a good point.
Okay. So,
Yeah.
all right. So here's the first member. So we've got, and we're gonna assume they're massless in comparison to the load that you're using. Okay. So the mass of the actual members is insignificant, is negligible. Okay. Now, if you have a pivot, you've got an X and a Y component. We don't know what it's doing. It could be, we're guessing at this point. Okay. And it's probably not horizontal or just vertical. It's probably doing both. Okay. So the way you guess is you pretend like this doesn't exist, like this all of a sudden was disappeared. Which way would this thing move? Because this is detached here. Probably like go.
Yeah.
Okay.
If that was detached to the,
Okay. So I'm going to say I've got a F1Y. It's a Y component. And then an X component is going to fall away. So I'm going to say it's holding that against the wall. So F1X. Okay. And then here you have a pivot, a pin. Anytime you have a pin or a pivot, you have the same thing. Now, we know that the sum of the forces on each of these members has to be equal to 0.
So we know the X direction.
So the X direction is probably this way. And that's X, Fx2. And if we took this out, it's going to fall this way. So F2y. Good with that? Cannot assume those Fy's are equal. Okay. Now, so we're looking at the forces acting on the member. Not what the member is doing, but what forces are acting on the member from the hinge. Now, this is the most crucial part of this. You can guess and guess incorrectly and still get the right answer. If you guessed wrong, your answer is just going to be negative, and that just means hey, the force is going in the other direction. But this, what I'm about to show you, if you mess this up, you're toast. Okay, this has to obey Newton's third law. Has to. Okay, so this is still the same force, just you have force 2x and force 2y. That has to be in the opposite direction of that and equal magnitude. So
as long as you put them opposite, you're okay though.
yes,
Mess up what
yes.
you just have to mess up twice.
No.
If you mess up that one, it doesn't matter if you got it.
Okay, does that make sense? You can guess initially, but when you have a joint here, these have to be Newton's third law. You can random arrows until you get to this point here.
Okay.
Okay.
You construct random arrows such as they fail.
What is F1 and F like?
So F1, this is the force from the hinge on the member. Is F1. This is the force on this member from this pin here. Okay? And so here down at the bottom, if I took this hinge away, it would fall down. So I'm going to say there's F3y.
For this one, you could have done.
And I'm just gonna assume that this is right. I need some of the forces in the X direction to be equal to 0. This cancels that. Okay. I can also, so you have the sum of the forces in the X and the Y direction here and the sum of the torques. You have the sum of the force in the x and y directions here and the sum of the torques equals 0. You can also do a whole thing of like one whole thing and say force of gravity of the load, and then you have F 1y F1x. Here you have F3y and F3x. Okay, and you can do the sum of the forces in the x and the y directions, and the sum of the torques is all equal to 0. Now, all those systems of equations, you've got way more than you need, but those are all legitimate. Like you do this free body diagram, extended free body diagram of each member, and then you can do the whole. Sam.
Are F1x and F3x up there?
No, they are not.
No.
Nope.
How do you know that F3x is going right?
I don't. I guessed.
It's
I guessed because of process. Like here on the green one, I know that the sum of the forces have to be equal to 0. I guessed that this one is going to the left, then this one's going to the right because the sum of the forces have to in the x direction have to be equal to 0. These two cancel each other out. Newton's third law says I have to go that way, and then the sum of the forces in the x direction on this guy have to be equal to 0. So because this is going this way, I'm just going to make this one go that way.
Okay.
Since the bottom pitch goes to float on the wall, isn't that going to be a Newton's fourth pair with F3x?
Great question. These are the same, identical.
Yeah.
I did not make a free body diagram of the wall,
Right.
or of the hinge itself.
Right.
Sorry, ask your question again.
Okay, so there's going to be, we're finding the force that the bottom hinge exerts on the wall, which is going to be this way.
We're finding the force that the bottom hinge exerts on this member, not on the wall, but on the brace. Oh,
Question asks, how much force does the
Oh.
bottom exert on the wall?
good call. Yes, that'll be Newton's third law pair.
Cool.
To
That's
that.
why we know it has to go this way.
Yes,
Because it's going to be the opposite.
yes.
Wait, what's gonna be?
The
force
F
exerted
To answer the question, I'm
Oh,
looking for.
yep.
I'm actually looking for the resultant of these two.
Oh, yeah, true.
Okay.
Which makes sense because it's.
And it's going to be
Yeah.
going
Right. Up to the left.
down like that. Is the force on,
Wait, but is any of if none of F the y direction wouldn't be exerted on the wall? So
It
we could
is.
just use
there? Okay, so is there a y component that the wall exerts on this
breaking
thing?
up the force pieces. Yes, but if you're breaking it up into the x, isn't the x component just what they're exerting on each other? So isn't the x component the answer?
Nope.
No.
It's but like this is exerting force both up
Uh-huh.
and to the right.
Okay.
Together.
The wall is exerting force.
Okay. Therefore, the member, the hinge, exerts the force down and to the left on the wall.
Okay.
Okay.
If we do
Right.
the conjoined as one, I assume if we screw up the directions on that, we're still all good.
You're all good because there's no Newton's
Right.
third
It's just
law.
the internal pairs have to be the same.
Right. Does everybody understand why we don't have to worry about the joint here if we look at the whole thing?
Yeah.
Okay. Okay. So you'll have a mastering assignment due in a week.
Hi, Miss Brenda. I was reading the one under physics and like,
Wait.
do it tomorrow.
Can
I
you
wanna do
like
my master.
solve this based on what you're given? And do you need like more stuff?
Nope, you got it.
Sure.
You know this. That's and the length to the 3069 triangle. So you're gonna make. I would make this 2L, this L, and this square root of 3L.
And then you just do like forces in x versus the y and torque.
Yep.
Oh, you still would have to do
Wait, but how
You
would
still
do
do torque, yeah.
torque?
What?
How would you do like torque?
Okay, so I would pick that to be my pivot. So you go mg over L over 2 minus F2y times L equals 0.
That's what I haven't. I've been doing lots of
That
Do you have to do it for all of them? Like the torque and the forces and the
the way it's
like all three?
stuff on the biggest end.
I mean, you can do torque stuff.
Are you still
Setting
recording?
like that bottom.
Yeah,
thing.
still recording.
So
So you can, I mean, you can make this your pivot, which I would, because that's easy,
Right, that's easy.
and this is easy.
Then all you have, that's super easy.
Yeah.
Wait, so
All you
that
have is
can't.
two things.
This can't. There's no
But that
torque
one
here. This one you have torque.
So it's just F3X and then.
Do you have
So
to like
this-
use all of them to do it?
No, this would just be. No, you don't have to. It is a lot of work. And welcome to statics in college.
This is
Yeah.
why I'm not going to civil.
Well, you had whatever you're engineering, you're probably gonna have to take statics.
Arrow, everything moves.
No, you're gonna. It's a requirement. So this makes it go that way. That's gonna make it go that way. So then minus F3x times. And
It's all for
you're there.
Wait, do you not?
Oh.
Oh,
Because
I
that's,
made
Oh my
that
god,
my
that
pivot.
makes sense.
Made that my pivot.
that's the radius. That's the radius. Okay.
That's super simple.
Yep. So, yep. So you look for those.
For the easy.
Look for the easier route.
You could also solve for